Good afternoon, everyone. Welcome to the 11th week of the structure analysis course, in which we will deal with the problems related to structure analysis. Let me share my screen first, then we will tell you the topics to be covered during this current week. I hope the screen is visible to everyone. So let's get started. So I welcome you all to the 11th week of this problem solving session related to structure analysis course, wherein we are dealing with the problems that are needed to be solved for the content you have covered during the current week. So my name is Pranav Mahajan. I am a PMRF scholar in Structure Engineering Division, Department of Civil Engineering from IIT Madras. So this opportunity is provided to us by NPTEL, wherein we will try to solve your queries as well as the problems related to the structure analysis course as well as the topics that are covered during this current week. So let's recap what we have covered from week 1 till week 10. So first of all, we have started with the analysis of statically determinate structures, wherein in week one we have started with the defining the reaction forces in the uh, beams, frames, trusses, how to determine the reaction forces. Then we saw that how we can determine the shear force as well as the bending moment diagram throughout the length of the beam or the frame, and then we have tried to establish the criteria for stability and the determinacy of the structures. Then we have moved to the V2, wherein in V2 we have seen the problems related to trusses, and in that we have told that the truss is a two-force member. What is a two-force member? The two-force member is a member which can handle compressive as well as the tension force. No bending moment is permitted throughout the length of the member. So how to solve that problems? So we have seen that we have solved that problem related to method of joints as well as method of sections. So to solve the unknown forces that are there in the truss members, we take a particular joint, apply equilibrium equations, and the number of unknowns should be less than the number of equilibrium equations. Then method of joints can be applicable. So in case the structure is very large and we are required to calculate the force of a particular member, then in that case we use method of section. So in method of section, we divide the structure into two halves using the cutting plane, and we apply the summation of moment at a particular point equal to zero, so that we can calculate the unknown force that is there in the truss members. Later on, we have moved to the calculation of the deflection in the trusses using method of virtual work using unit load method, in which we have seen that if we apply the unit load in a particular direction, whether it is horizontal or vertical, we are able to calculate the deflection in that particular joint using unit load method. Then we have shifted from truss to the beams, that how we can calculate the deflection and slopes in beams and frames. So we have utilized the method of moment area method, conjugate beam method, and virtual movert method to determine the deflection at particular joint or particular point in a beam or the frame member. So this is what we have covered in the statically determinate structures. Later on, we have moved to the influence line diagram. So in what is influence line diagram? Whenever a frame or a beam is subjected to moving load throughout its section, so the reactions as well as the shear force and the bending moment developed in the section due to that moving load will give you the influence line diagram for that particular joint. So we determine these reactions as well as shear force and bending moment using Mueller-Bridge law principles. So later on from week 7, we have shifted to the analysis of statically indeterminate structures. So we started with the force and stiffness methods. So we have defined the various methods that come under the category of force method. We have also defined some methods which come under the category of stiffness methods. So we have told that in force method we are required to calculate the unknown forces that are there in the member using the known displacement that are available to us. Whereas displacement method is vice versa to the force method, wherein we will calculate the displacement, unknown displacement in the member using the known forces that are available to us. So starting with, we have started with the trusses. So when we have statically indeterminate truss, how we have done that? So we have utilized the method of consistent deformation, where then we have shifted for to beams also, and we have utilized the unit load method to determine the unknown force that are there in the member using method of consistent deformation in beams. We have also utilized the concept of three moment theorem, which is based upon conjugate beam method, that how we derive the whole uh, equation related to 3-point bending. So these 3-point theorem is generally applicable in case of continuous beams. When we have more than two spans in a particular beam, then we will apply this three moment theorem and determine the unknown moments that are there at a particular joint using this three moment theorem. In the last week, we have utilized the concept of slope deflection method. So in that, we have utilized the slope deflection equation to calculate the end moments in statically indeterminate structures. So what we'll cover in this current week, we will solve the problems using moment distribution method. So what we do in the moment distribution method? So moment distribution method is also known as Hardy cross method. When what we will do, we will try to solve the problems and try to calculate the value of end moments using this carryover moment, as well as the distribution factors in the continuous beams. So first of all, we will define we will define absolute stiffness for various members. So for absolute stiffness, let's say we have a cantilever beam available with us. So in this is a prop cantilever. So in this, the deflection will occur like this. So it means there is a moment that is occurring in this point in clockwise direction, that is MAB, and the slope in this is theta AB. So in this case, how you define? So you define two moments, that is MAB and MBA. So here MAB will be equal to 4EI upon L into theta A, whereas MBA, that is the carryover moment, and it will be half of the moment that is applied in the in the cantilever beam, and it will be 2EI by L into theta A. So in this case, we also can write that MAB is equal to K times theta A. So this K will be equal to 4EI upon L, and this we call it as the absolute stiffness for this beam. However, this carryover moment MBA is half of MAB. So how we define it? We define it as a carried over moment at B due to MAB. So in this case, MBA is equal to CAB into MAB. So this CAB here is coming out to be 1 by 2, and this is your carryover factor. Similarly, if you are about to determine these moment in case of a hinge beam, then how you will define that? So in case of hinge beam, suppose MAB is the applied moment. So in that case, MAB will be equal to 3EI by L into theta A, and MBA is equal to 0. So here K is equal to 3EI by L, and carryover factor CAB is equal to 0. Because the applied moment whole is taken up by the support that is provided in AB section. So no carryover moment is generated due to the applied force at A. This happens because in this the moment is allowed in the section in A in at support A as well as support B. Whereas in case of that cantilever beam, we are allowing the rotation to happen from A to B. But at B, since there is a fixed support, no rotation is allowed. So additional moment will come in reverse direction, which will keep the net moment at that fixed end to be equal to 0. That's why carryover moment is generated in case of a fixed beam. Whereas in case of hinge beam, since both the supports are allowed for rotations, so whenever you apply the rotation at a particular end, no carryover factor will be generated for the other support that you are provided. So what will happen if you apply in prop cantilever beam moment not at the hinge end, but if you try to apply the moment at the fixed end. So if you apply the moment at the fixed end in this, suppose MBA, so in this case, no moment will be transferred to uh, this to A to support A. So in this case, MBA CBA will be equal to 0. Okay. So you have two cases where CAB is equal to 0 when you have far end hinge. Okay. So remember, whenever the far end is hinged, you have the CAB equal to 0. Whenever your far end is fixed, your CAB is half. Okay. So now let's take a problem related to a continuous beam and then we will try to solve that. So suppose we have a long continuous beam which is fixed at one end and fixed at other end also, and in between hinge support is provided. So in this case, you are providing a UDL in one half of the span and a concentrated load at other part of the span. So let's say this length is 5 meter. this length is 2 meter, and this length is 3 meter. Okay, so this is your continuous beam. So in this case, how the deflection of the beam will occur? So beam will deflect like this. So if I make the deflection profile, it will somewhat look like this, and it will further continue here and will go like this. Okay, if I separate both of them, how they will look like? So here the moment will be applied, that will be MBA, and due to that moment, the beam will be deflected in this shape like this. Yeah. So in this case, when there is concentrated load applied, so in this case, the moment is applied in clockwise direction. So in this case, the deflected shape of the beam will look like this. So if we take the two spans, let me add a slide. So if we take two spans here, KBA, since the far end is fixed, so it will be 4EI BA upon LBA, that will be equal to 4EI upon 5. Whereas in KBC, in BC part, it will also be same 4EI BC upon LBC, that will also be same 4EI upon 5. So now if you are required to calculate the distribution factor, so the distribution factor, how we are required to calculate it, it will be KBA divided by KBA plus KBC equal to 4EI upon 5 divided by 4EI upon 5 plus 4EI upon 5 equal to 1 by 2. Similarly, this is for BA. If for BC we are required to calculate it, so BC will also be same, so it will also be 1 by 2. Okay, so carryover factor, that carryover factor in this case, CAB is equal to CBC, it, it is equal to 1 by 2. Yeah. So this is how you calculate the distribution factors. Okay. So what are the steps you are required to be calculated to solve any problem? So steps for solving any problem. So step one is calculation of fixed end moments. Next step is after calculating the fixed end moments, then calculate the unbalanced moment that is there in the structure. So your next step is calculation of unbalanced moments. So if we move to step 3, so step 3 will be determining the balance moment. Okay, then you will determine the balance moment, that will be the negative of the unbalanced moment that is there in the structure. Step 4 will consist of distribution of this balance moment. So distribution of the balance moment depends upon the distribution factors that are there on the two sides of the joint. Based on distribution factor. In step 5, what you will do, in step 5, you will carry over the distributed moment to other ends. So carried over of the distributed moments. In step 6, what you will do, you will add the moments generated in step 1, step 4, and step 5. Okay, these are the steps that you are required to be calculated to solve any problem related to a moment distribution method. So we will try to solve the same problem that you have seen for the carryover factors. We will use this same problem and then solve them using this method. So let me take, or I will draw again. No, I can take this figure also. So I will take this figure and we will use this figure for solving the problem again. Okay, so this is your figure. In this, we have calculated the distributed factor BA equal to, so I think distributed factor we have not calculated. So in this case, your distributed factor dBA will be equal to, okay, so we'll take another problem, not the same. I will remove this here. Okay, problem is same, but in this case you have a hinge here, not the fixed end. So now your deflected profile will look like this. Okay, so in this case what will happen, your carryover moment will remain same, but your d distribution factor will change. So first, the distribution factor in this case will be uh, for dBA, it will be 4EI by L divided by 4EI by L plus 3EI by L. So that will be equal to 4 by 7, and dBC will be equal to 3EI by L divided by total total distribution factor, that is 4EI by 5 divided by 3EI by 5, and that will be equal to 3 by 7. Okay, and your carryover moment, that is CBA, is equal to CBC and it will be equal to CCB equal to 1 by 2. So let me mark it here, that is this is A, B, C. Okay. So we will make a table, and from that we will solve the problem related to this. Yeah. So let's say this is your support A, this is your AB span, this is your BC span. What are the distribution factor we have calculated? Distribution factors are, here is 4 by 7, here is 3 by 7. So in step 1, you are required to calculate the fixed end moments. So step 1 is fixed end moments. So that will be MABF will be equal to minus 3 into 5 square divided by 12, and that is coming out to be minus 62.5 kilonewton meter. And your MBAF will be equal to 62.5 kilonewton meter. Your MBCF will be coming out to be minus 7.2 kilonewton meter, and your MCBF is coming out to be 4.8 kilonewton meter. Okay. So first we will write the fixed end moments here. So that will be equal to, so let me correct it. It is not 62.5, it is 6.25. Okay. So this is 6.25 and this is also 6.25. So that will be minus 6.25. Here it would be 6.25. Then here for BC span, it is coming out to be minus 7.2 and 4.8. So this is your fixed end moments. Now we will distribute the unbalanced moments. So in this case, your difference is minus 7.2 plus 6.25. That will be equal to minus 0.95. So we will divide the 0.95 based upon their distribution factors. So we will multiply 0.95 into 4.7. We will get as 0.54 here and then 0.41 here. Okay. So since this end is hinged, this will be minus 4.8. This is your distribution of unbalanced forces. Now these will be carry forward. So we will write it as that this is distributed balance moment. Okay. Now this will be carry over to the other ends. So that will be 0.27. So 0.27 will come here. 0 will come here. 4.2, there will become 2.4 here, and here it will become 0.21. So this step will give you your carried over moments, and this step will continue till the unbalanced moment will converge and reaches to a very lower values. Okay, so now 2.4 will be divided based upon their distribution factors. So it will come as 1.37 and 1.03, and now here it is 0.21. It will become minus 0.21. Okay, and when it is carried over other end, it will become 0.68. Here it will be 0. Here it will become minus 0.11. and here it will become 0.52. Now again, since these are carryover moments, we will make these unbalanced moment to be balanced again using balance moment consideration and distribute them based upon their distribution factor. So that will become 0.06. This will become 0.05. This will become minus 0.52. Okay. So by this, since the values are now very less, we will end this problem. And remember, whenever you are ending any problem, end them on distributed balance method, balance moment, not on carried over moment. Otherwise, it will not will satisfy your problem. Okay. If you add all of them, you will get the value as minus 5.29. Here you will get 8.22. Here you will get minus 8.22, and in this case you will get the value as 0. So by this you will end the problem here. So now you have calculated the n moments. If you plot them, how it will look like, let's see that. So first you plot the values related to the applied loads. So this is the applied loads values, and if I, yeah, and due to the concentrated load, yeah, it will look like this. Now you apply the unbalanced the n moments that you have generated in negative direction. So your values will be, so here it will be 5, here it is 9 or 8.22. Yeah, and at end it is 0. So if we join both of these points, so if we join both of these points, yeah, so the area which is coming in the shaded region will give you the bending moment diagram. So this shaded region area is your bending moment diagram. Here, this region is negative, this is positive, this is negative, and this is positive. Here, the maximum values you have obtained is, in this case, it is 9.375. This is from the origin, not from the point where we have calculated. This is 8.22, this is 12.5, and this is 5.29. So that's how you calculate the values for the bending moment using moment distribution method. So in case of frame, how you will do that? That is, the procedure will be same. Let's look for one problem related to frame. So suppose you have a frame with UDL applied in the horizontal span, and the loading value here is 7.5 kilonewton per meter. Okay, so this is your end A, B, C, and D. Let the length be, this length be 5 meter, this be 10 meter, and this will be 5 meter. Okay, now we will calculate the, what we say, we will calculate the carryover, uh, the distribution factors, or first we will calculate the stiffness. So KAB will be equal to 4EI by 5. Then your KBC will be equal to 4EI by 10, that is 2EI by 5. Now your KCD will also be equal to 4EI by 5. So if you calculate distribution factors, then DBA will come out to be 4EI by 5 divided by 4EI upon 5 plus 2EI upon 5. We take only for the particular joint, not for the whole beam. Okay. So we are considering only a joint. That's why I have not added the 4EI by L that is additionally there. So it will come out to be 4 by 6. Or you can write it as 2 by 3 also. Then for BC, it will be 2EI by 5 divided by 2EI by 5 plus 4EI by 5, and it will be equal to 2 by 6. Similarly, your DBC will come out to be 2 by 6 equal to 1 by 3. Your DBC we have already calculated. So your DCB will come out to be 1 by 3, and your DCD will be equal to 2 by 3. In this case, your carryover factors CAB equal to, sorry, CBA plus CBC plus CCB, CCD will be equal to 0.5. Okay. So now let's calculate fits and moments. So what will be the fits and moments? So MAB, since two spans MAB and MCD will be equal to 0, so your MAB, MBA, and MCD and MDC will be equal to 0. And another thing is MBC and MCB will be equal to 62.5 kilonewton meter. Now we have calculated all the distributed factors and fits and moments. Now made the table and we will try to calculate the end moment values. So first span will be AB, next span here will be BC, and then it will be CD. So this is AB, this will be your BC, then it will be CD. And here your distribution factor is 2 by 3. Here it is 1 by 3. In this case, here it is 1 by 3, and here it is 2 by 3. Now first we will write the fifth end moments. So in this case it is 0, 0. Here it is minus 62.5. Here it is 62.5. In this case here it is 0 and 0. Now we will distribute this unbalanced moment as a balanced moment based upon the distributed factor that is available with us. So here it would be 41.67, and here it will be 20.83. Similarly, here it will come as minus 20.83, and in this case it will be 41.67. Now next step is carry forward of these moments. So that will come out to be 20.84, and in this case here it will be 0, and here it will be 10.42, and this is positive 10.42, and here the carry forward would be negative of 20.84. Okay. Now again you will distribute this unbalanced moment. So 10.42 is distributed as 6.95 and 3.47. Same here as negative 3.47 and minus 6.95. And the carry over moments will be half of these moments. So that will come out to be 3.48, and here it will come out to be minus 1.74 and 1.74, and here also 3.48. Again, this unbalanced moment will be distributed. So it will come out to be 1.16 and 0.58, and in this case it will be minus 0.58 and minus 1.16. Now next step is to distribute this unbalanced moment. It will come out to be 0.58, and in this case it will come out to be minus 0.29 and 0.29, and it will become minus 0.58. Again distribute this unbalanced moment. It will come out to be 0.19 and 1.0, minus 1.0, minus 0.19. Distribute among the distribution factors available to you, and then carry over to the other ends. It will come out to be zero point 0.1 minus 0.05. Here it will be 0.05. Here it will be minus zero point 0.1. And again we will distribute this unbalanced moment. It will come out to be 0.03, 0.02, minus 0.02, and minus 0.03. And finally, since now the values are very less, we will add them up and calculate the end moment. So in this case, the values are coming out to be 25.1. Here it is 50. Here it is minus 50. Here it is 50. Here it is minus 50. And then 25.1. So these are our end moments, and if we plot them, how it will look like. So first draw the frame. So this is our frame. Now first one is positive, so 25 is in positive direction like this, and here it is 50, so it would be like this. So 50 and 50 will be divided same, so here it is also 50, and here it is also 50. Yeah, same in another side. Right, now we will also make the loading that is there, that is fits. We have the um, sorry, UDL in the section BC, so that will also come into picture. That will be like this. Okay, so now your area will be this area. So your shaded area is the bending moment profile for this frame, which is the sum of the end moments as well as the applied loads that is there in the span BC. So the values here, it will be 93.75, 50. Here it is also 50. Here it is 25.1. Here it is 50. Okay. So this is your the bending moment diagram for the frame that you have considered for the solution of the problem using moment distribution method. Now let's solve some problems related to what we have covered during this current week. Okay. So the question one says that calculate the distribution factor of moment at joint E for span EA and ED. For EA and ED, we are required to calculate the distribution factor for the frame that is shown in the figure. EI is same for all the members. So let's calculate the distribution factors. So for that, we are required to calculate first that what will be the stiffness, absolute stiffness for that particular span. So let's write. So for span EA, so KEA, since the far end is fixed, so it will be 4EI upon L. So L in this case is 2. In span ED, it is hinge. So KED will be equal to 3EI upon, what is the length? Length here is 3. So 2. So length, so 4EI upon, this is 2 meter. This is 2 meter. Okay. And this is 3 meter and 1 meter. Okay. So these two we have calculated, but in this span we are also required to calculate others also. Then only we can calculate the distribution factors, because without calculating for span, absolute stiffness for span EB and EC, we can't calculate the distribution factors. So for KEB, it will be equal to 3EI upon 1 because here the length is 1, and KEC will be equal to 4EI upon 3. Okay, now we can calculate the distribution factors. So distribution factor for EA will be equal to KEA is 4EI upon 2 divided by 4EI upon 2 plus 3EI upon 2 plus 3EI upon 1 is 3EI, then 4EI upon 3. So your total DF for EA will become 12EI upon 47EI, and then if you solve them, it will become 12 by 47. So for EA, we have calculated. Now we are required to calculate for E, EB or ED. For ED. So for ED, how we will calculate? So for ED, so distribution factor for ED will be equal to 3EI upon 2 divided by the total. So total we have already calculated it as 47 EI upon 6. That will become 3 by 2 into 6 by 47. That will become 9 by 47. So these are the two distribution factors you are required to calculate for this frame, and we have calculated that. Now let's move to another question. So the question is same. Now in this question, you are required to calculate the distribution factor for EB and EC. So first we have calculated for EA and ED. Now you are required to calculate for EB and EC. So your DF for EB will be equal to, this is 3EI divided by 47 upon EI upon 6. That will become 18 upon 47. Okay. Similarly for EC, how you will calculate? So your EC will become, here it is, you are having 4EI for EC. You are having 4EI upon 3 divided by 47 EI divided by 6, and you have made it to 4 by 3 into 6 upon 47, and that will be 8 upon 47. Okay. Now you have calculated the distribution factors for span EC, EA, ED, and EB in both the questions. So this is what you are required to be calculating in this particular question. Now next question is, you are required to calculate the absolute bending moment at A for the continuous beam ABC. So now in this case, you are required to calculate each and every step using the moment distribution method. So first we will solve for absolute stiffness. So here we have KBA, far end is fixed. So it will be 4EI by L, that is 5. And here in KBC, far end is hinged. So that will be 3EI upon 2.5. And if we write it as, so it will be 6EI upon 5. Okay. So your distribution factor for BA will become 4 upon 4 plus 6. That will be 2 upon 5. And your DF for BC, you can also write it as 1 minus dBA, that will become 1 minus 2 by 5, and that will become 3 by 5. Okay. Now calculate the fixed end moments. So fixed end moments for span AB will be equal to MABF will be equal to minus 12 into 5 square divided by 12. It will be equal to minus 25 kilonewton meter. And for MBA, it will be equal to 25 kilonewton meter. Now we have calculated distribution factors as well as we have calculated the fits and moments. Now let's draw the table for solving the problem. Hmm. So first we have only these two spans. So here we have A, B, and there it is B and it is C. Now your fits and moments are minus 25, 25, 0, and 0. Distribution factors you have calculated as distribution factors we have calculated as one is 2 by 5 and the another is 3 by 5. So this is 2 by 5, this is 3 by 5. Okay. Now you have to divide this 25 based upon the distribution factors. That will be distributed as minus 10, and here it would be minus 15. Okay. Now this 10 and 15 will be carried forward as minus 5, and here it would be minus 7.5. Now what is your total? So total here is 30. Here it is 15. Then you have minus 15. Then you have minus 7.5. Okay. Now since the central part is now balanced, but you have an unbalanced moment of 7.5 at support C, because that C is hinged. So that should be 0. So what you will do, you will add 0.75 in this to make it balance. If you add 0.75 here, so the another carry forward that will happen, that would be 3.75 here. If 3.75 is added here, so now what are the current value of the moment? So it is minus 30, 15. So that is minus 11.25, and here it would be 0. Now we have in central part a difference of around 3.75, and this 3.5 we have to distribute based upon the distribution factors. So how we will distribute? So we will distribute it as minus 1.5 and minus 2.5. Okay. So then these will be carried forward as minus 0.75, and in this case it will be minus 1.13. So again the unbalanced moment altered at the end. So we will remove this unbalanced moment. So how we will remove that? I'm not adding now. I will directly solve the problem. So if I add this 1.13, it will give you the value here as 0.57. Okay. Now, if you distribute the value, what you will get? You will get minus 0.23, and this is minus 0.34. Okay. And when it is carried over, it would be minus 0.12. And in this case, we are not doing because we are uh, solving this problem up to this end only. So we will keep it like this. So what will be our end moments? So where our end moments will be, let me close it first. Yeah. So your end moments here comes out to be minus 30.87, and this is 13.27. This is minus 13.27, and this is 0. This is what we are required to be calculated. If you want more precise value, you can again proceed further and then try to calculate the values based upon the distribution factor available with you. Okay, so what is required to be calculated? So in this, you are required to be calculate the absolute bending moment at A. So you got absolute bending moment as 30.87 kilonewton meter. Now let's solve another question. So another question, what it says that in this you are required to calculate the reaction force at support C for the continuous beam. So since we have calculated the moment, so these moments will also come into picture because we have continuous beam. So let's draw the free body diagram. So you have this. You will be having VA here. This is your VA. This is your VC, and you are having the negative moment here. So I will write it in the anti-clockwise direction, the value as 30.87. And since the value here is positive, so I will write here is in clockwise direction 13.27. Here the load is 12 kilonewton meter for 5 meter length. So apply summation of moment about A is equal to 0. What you will get? You will get anti-clockwise moment as minus 30.87. Okay. And then VC will also be negative. So VC into 5. And then you have positive 13.27 plus 12 into 5 into 2.5. This whole is equal to 0. If you solve for VC, VC or VB? Here it will be VB, no? Yeah, VB. Let me correct it. It is VB. Yeah. So VB. So your VB will be 26.48 kilonewton. So if this is 26.48, use summation of V equal to 0. That will give you VA equal to 60 minus 26.48 equal to 33.52 kilonewton. So this is your reaction at support A, but you are required to calculate reaction at support C. So take another span also. In this span, your end moment here is anti-clockwise 13.27. That end is 0. So you are having VB here and since and this VC will be negative. So take summation of moment about B is equal to 0. So it is giving you minus 13.27, okay, plus VC into what is the distance? So distance here is 2.5. 2.5 equal to 0. So your VC will come out to be 5.31 kilonewton. Okay. And similarly, your VB will also come out to be 5.31 kilonewton. So your total reaction at B will be equal to 26.48 plus 5.31 equal to 31.79 kilonewton. But since in this question they are only interested in VC, so your VC is 5.31 kilonewton. Okay, this is how you solve the problem for moment distribution method for any beam frame. So for frame also the concept is same. So let's solve one problem for frame also. So in this case, you are required to calculate absolute bending moment for point C. So this question is similar to previous question that we had solved, but in previous question we are interested in calculating the absolute bending moment at A. In this question we are interested in calculating the absolute bending moment at C. So let's solve it. First we will calculate the absolute stiffness factors. So your KAB will be equal to 4EI upon 18. Your K, not write it as AB, we will write it as BA because only at B we are required. So in this, BC will be equal to 4EI upon 9. If I make it so, it will be 8EI upon 18 so that the denominators will be same. So your distribution factors will be, so DF for BA will be equal to 4 upon 4 plus 8. So it is 4 upon 12. That is 1 by 3. That means your DBC will be equal to 2 by 3. Okay. Now your fits and moments will come out as MABF will be minus 4 into 18 square divided by 12, and this value is equal to minus 108 kilonewton meter. Similarly, your MBA will be equal to 108 kilonewton meter. Now we will make the table and solve for this whole frame. So we have only, okay. So this is your A, B, one span, B, C, another span. Distribution factors you are having as 1 by 3 and 2 by 3. So 1 by 3 and 2 by 3. The fits and moment values you have calculated as minus 108, 108, 0, and 0. Okay. Now distribute this unbalanced moment. That will be minus 36, minus 36, and minus 72. This will be carried forward to other end. That will become minus 18 minus 36. Okay. Now we will add all of them and we will get one value. Minus 18, that will be 72, and this will be 72, that will be minus 36. So in this case, at ends the values can come because other ends are fixed. So these will be your fixed end moments. So they are interested in the end moment of B. So at B, you are getting as minus 36 kilonewton meter, and that is your final answer. Okay, so in this question, it is mentioned that absolute bending moment at C. So absolute bending moment at C, it will be equal to minus 36 kilonewton meter. Okay. Now what is the next question? In next question, they are asking to calculate the absolute shear force at A. So similar to what we have done in previous question, we will make the free body diagram. So in this case, uh, this is your VA, this is your VB, and you are getting the moment as negative 18. So this is your 18, and sorry, I think I have not added here. So this value will be minus 126. Rest are equal. Okay. So this will be 126. Okay. And here it is 72 in clockwise direction. Total length is 18 meter. Now use summation of moment about A equal to 0. What you will get? You will get VB is minus 126, then plus 72, then this will be negative VB into 18 plus this is 4 kilonewton meter. So it would be 4 into 18 into 9 equal to 0. If you solve for VB, you will get VB as 33 kilonewton. And if you take summation of V equal to 0, you will get VA equal to 18 into 4 minus 33. So you will get VA equal to 39 kilonewton. Okay, this is how you solve the problem. So if you want to calculate horizontal force, suppose it is also mentioned that you are required to calculate the horizontal force in span BC. So how you will do that? So in this question, it is negative, so anti-clockwise. So this is anti-clockwise, and here it is clockwise. No, sorry. Here it is also anti-clockwise because both are negative. So this is 72. This is your 36. What is the length given to you? So length here is 9 meter. You are having HB here. So this is your HB. This would be your HC. So take summation of moment about B equal to 0. If we take vertical forces, that will not affect the problem because that will be along the axis. So that's why we're neglecting it. So moment is negative, minus, minus, and then it would be plus hc into 9 equal to 0. That would be 12 kilonewton. Okay, that is how we will calculate the reactions in the frame using moment area method. Oh, sorry, moment distribution method. Now moving to next question. In next question, you are given another frame and you are required to calculate first the distribution factors for the given problem. So how we will do that? Let's see. So in this case, we start with BA fixed. So that would be 3EI upon 15. Then we move to KBD. That would also be 3EI upon 12. Then KBC. That will be 4EI divided by 12. So let's directly write the distribution factors. That will be easy for you. So if we directly write the distribution factor, so your DF for BA is coming out to be 3 upon 13. So in this case, I directly require the distribution factor for each of the case. So I will directly write the distribution factor, uh, not for BC, for each and every span. So in this case, your DF will for BA will come out to be 3 upon 13. Your DF for BD will be equal to DF for BC, and it would come out to be 5 by 13. Okay, and your rest DFs, that is DF for DB for hinge, it is 1. Then your DF for AB, again it is hinge, so that will be 1. For DF of CB, since that is fixed, so that will be 0. Okay, so all the distribution factors that were required for these calculations we have written in these slides. And now next is you are required to calculate the bending moment at C. For bending moment at C, let's first calculate the fixed end moments. So fixed end moments, so your fixed end moment F, your MAB would be equal to minus 2 into 15 square divided by 12, and that value come out to be minus 37.5 kilonewton meter. Okay, and this value is equal to minus BA into F. Now next is for span BD. So your MBD F will be equal to minus 2 into 12 square upon 12. That will be equal to minus 24 kilonewton meter, and that will be equal to minus M dB into F. dBf. Okay, and since for DE there is a cantilever, so that will give us negative moment. So our MDE F will be equal to minus 8 into 8, that will be equal to minus 64 kilonewton meter. Rest are all zeros. Okay, now we will make the table and solve the problem. So first we will write the joints, then we will write members. So let's write the members. So we have member AB, BA, then BC, then BC also we have BD, then we have at B we have BC, BD, and then we have DB. Okay, then we have DE, then we have additional, that is CB. So we will mark them as this is our joint A, these three are at joint B, and these are at joint D. Okay, now we will write the distribution factors also. So their distribution factors are 1, 3 by 13, 5 by 13. In this whole case, it is also 5 by 13. This is 1, this is 0. So your fits and moments you have calculated. So that value is minus 37.5. Here it is 37.5. It would be 0. Minus 24. Here it is 24. Then because of the cantilever, it will come out to be minus 64. And here it is 0. Okay. Now we will divide the unbalanced moments based upon their distribution factors. So for joint B, we are having the value around 13.5 as the unbalanced moment. So we'll divide them based upon the distribution factor. Here it will come as minus 3.12, minus 5.19. Here it also 5.19. Okay. Now this 5.19 will now then be carried forward to DB and CB. So that will be minus 2.6 and minus 2.6. So these are the carried forward movements. Now I am writing directly because it would be easy for me then to solve the problem. So for after first stage, the values here, no. Now let's write, since here it is also joint is hinge, so unbalanced moment comes out to be 37.5. That will become 18.75. Okay, and here it is 42.6. That will become 21.3. Okay, now these unbalanced moments are further divided, so that will become, so at joint D it will be 21.3 plus 18.75. These are the unbalanced moment. That will be divided as 9.84 minus 1.48. Sorry, here it will be minus 15.4. Then it will be minus 15.4, and then half of them will be carried forward as minus 7.7. and here minus 7.7. Now this 7.7 is then added as positive 7.7, and then it will be carried forward as 7.3.65, and then again it will be distributed as minus 0.89, minus 1.48, minus 1.48, and minus 0.74. No, these three are distributed, and then these are carried forward as minus 0.74 and minus 0.74. Okay, again this 0.74 will be balanced out as positive 0.74, and 0.37 will come into picture. So if 0.37 come into picture, it will become minus 0.09, 0.14, 0.14, and their carried over factor as 0.07 and zero 0.07 and 0.07. Okay, this 0.07 will then be added back as plus 0.07, and that will become 0.04 as the carried over factor, and it will become minus 0.01, minus 0.02, and minus 0.02. So these are the distribution factors. And now I think we should end this problem here. Okay. So we will do the final total here. So our final values here are coming out to be 42.8. Here it is minus 23.23. Here it is minus 20.67. Here it is 64. Here it is minus 64. And here final value is mhm, sorry, I think AB is not there. No, AB is 0 because it is hinged end. So this is 0. This is 42.8. This is 22.23. This is 20.67. This is 64. Here it is minus 64. And here it is 11.11. So these are your end moments that are developed in the section for this beam, for this frame that is given to you. Okay, and in this you are required to calculate absolute bending moment at C. So absolute bending moment at C is coming out to be 11.11 kilonewton meter. So this is your absolute bending moment at C. Okay. Now your next question is you are required to calculate the vertical reaction support at A. So similarly that we have calculated earlier, we will now solve the problem for this. So draw the free body diagram. So this will be your VA. This will be your VB. Here the moment is 42 0. So no moment here. And for AB it is 42.8. So 42.8. And length is 15 meter. So taking moment about A equal to 0, you're having minus VB into 15 plus 42.8 plus 2 into 15 into 7.5 is equal to 0. So your VB is coming out to be 17.85 kilonewton. If you are required to calculate VA, so this implies your VA will become 15 into 2 minus 17.85. So that will give you VA equal to 12.15. This is how we will calculate the reactions at ends. If you are required to calculate others also, we can calculate. So suppose in other beams, how it will be. So in this span, you are having 12 kilonewton meter. This will be VB. Then this is VD. Here the moment is 20.67 in negative direction and 64 in positive direction. So you will take moment about B equal to 0. Then your minus VD into what is the length? 12 meter into 12 plus 64 plus 12 into 12 into 6. I think this is 2. If this is 2, then this is also become 2. Okay. 6 minus 20.67 equal to 0. Then you will get VD as 15.61 kilonewton. Okay. So your VB will become 2 into 12, 24 minus 15.61. So your VB will be equal to 8.39 kilonewton. Okay, so if anyone wants to calculate the total value, then you can calculate the total value also of reaction at B. So for the span BC, so you are having the value as, so this is your reaction here is 22.23 in anti-clockwise direction, and here again it is anti-clockwise direction, that is 11.11, and due to that you will get the horizontal reaction force as 2.78 and 2.78. Okay, so this is your B and this is your C end. In case of cantilever, you already have this load. Okay, so you will be getting the value here as 64 kilonewton, and your VD will become 8. Okay, so VD will be 8 kilonewton. So if total VD, total reaction force at D you are required to calculate it, add both the reaction forces for the two spans BD as well as for DE. Okay. So by this we end the problems related to what we are required to be covered for moment distribution method. So in this week we have covered all the problems related to uh, moment distribution method for beams as well as in frames. So let's recap first what we have done. So we have started with the moment distribution method. We have told that the absolute stiffness when the far end is hinged is 4 EI by L, and in case of an hinge it is 3 EI by L. Then we defined few steps that are required to be uh, know before solving the problem. So first you will calculate fits and moments. Then after calculating the fits and moments, you also write the distributed distribution factors for both the spans at a particular joint. Then you will write the unbalanced moment based upon the at particular joint, what is the difference between the value that is available with you. Then you will determine the balance moment, distribute them based upon the distribution factor, and after distributing the moments, you will then carry over that distributed moment to other ends, and then you will add all the moment that you have generated. And if the at particular joint the moment is balanced, you will stop at that particular point. Otherwise you will solve that further and converge to a solution wherein wherein at a particular point that wherein you will reach at a particular point where the at particular point the unbalanced moment will be equal to zero. So we started with one problem for a continuous beam. We determine the distribution factor, carryover factor, and then based upon the fits and moment available with us, we have first write the first equal fits and moments. Then we have written the distributed balance moment, and then we have carried over the moment to the other ends. Then we have total and checked whether at particular joint the distributed moment are balanced. So if they are not balanced, then we again uh, proceed this till the point the distributed moments are balanced at that particular point. Okay. After that, we have uh, we have also determined the bending moments that are there in the particular continuous beam. Same thing we have done for the frame problem also. And then we have solved few questions. We have solved how to determine the absolute stiffness, then how to determine distribution factors for different spans based upon the end far end condition that is available with us. So this problem we have done for the uh, continuous beam, and then we have solved one problem related to frame, and then we have combined the frame problem with the cantilever portion and try to determine the end moments that are there in the structure based upon the distribution factor available with us, and then finally we have calculated the reaction force that are there at the particular joint. So by this, our 11th week is concluded. So if anyone has any problem, they can post in the in the discussion forum available in the Swayam app. The TAs will try to solve their queries as soon as possible. And by now, you are reaching in the final week of this structure analysis course. And now only the last week is pending, in which you will see how the direct stiffness method will be utilized in the solving of the problems. Okay, so if you have any doubt, you can ask now also. But I see there uh, you can write your problems in student discussion forum that is available on the Swayam app. And by this, I will end this session. Hope you have liked this session, and try to solve the problems related to moment distribution method. It will try to uh, solve your queries and increase your concepts as better as possible. And for any queries, you can contact the TAs available for this course. Enjoy your weekend. Have a nice day. Thank you.